Hello. So, this is our module 11 of the NOC course and symbolic logic. We have just finished by module 10 the syntax of PL or propositional logic, where you have learned how to combine propositions, what are the syntactically correct ways to arrange propositions to generate say compound propositions, and how to use the connectives properly. The symbolization was mainly an exercise to understand the operations of the connectives, where to put, where not to put, and so on and so forth. You have also learned the scope of the connective, but today onwards we are starting something called the semantics. If syntax is one of the important components, semantics is also an equally important component for any formal logic system. So, from module 11 onwards, what we are starting is semantics. Propositional logic semantics, I will explain what that is, but mainly what you are going to learn in this module is what does it mean to assign truth values to propositions, and then also we are going to learn how to construct a truth table. You may have heard the term truth table earlier also. Some of you may have done this truth table also, but together in this course we are going to learn the way we intend to do the truth table. You know, there are more than one ways to do them, but this is our way of doing the truth table. So, this is what we are going to learn today. So, first thing is, what is semantics and what do we mean by the propositional logic semantics? See, syntax, as I told you, gives us rules to form well formed sentences in a given language. It is the grammatical rules that tell you how to generate well formed propositions in a given language. What is the job of semantics? That once this well formed syntactically correct propositions or statements are done, how to assign meaning to them. So, meaning assignment or interpreting the well formed formulas or well formed statements of a given language, that is the task of semantics. So, semantics teaches us how to assign meaning to the well formed statements. If that is what semantics is, then what does propositional logic semantics do? And this is where we need to come through like this. It also assigns meaning to the well formed propositional logic statements, but the way to assign the meaning is like this, that each simple proposition is assigned an interpretation with a truth value. All right. Remember what I said earlier, that you can't have in PL any proposition that does not have a truth value. So, here you are, the beginning is that the simple proposition is assigned an interpretation with a truth value. For example, this is what we have been doing in the symbolization. So, this is your propositional constant, and we assign it some sort of a proposition or statement with a truth value. For example, Arctic Circle is in the northern hemisphere. That is a statement which has a truth value. So, that first thing is that we are taking the elementary units, the basic units, and we are trying to assign truth value to them. Okay. We are assigning them propositions which have truth value, and then compound propositions are born by the use of the connectives. Their meaning, the meaning of the well formed compound propositions are done by processes, semantic processes. One of them is the truth table. There are other procedures also. So, the same way does not work for the compound propositions. Why? Because the compound propositions here in this PL, they are all truth functional. So, the knowing the truth value of the components somehow is going to reflect back on the truth value of the compound proposition. So, one of the ways to assign the meaning to the compound proposition, as I said, is truth tables. And so, now our next stop would be to learn how to do this truth table, what truth tables are and how to construct the truth table. That is the goal of this module specifically. Truth tables. What truth tables are actually a mechanical method. It is a method that is sort of blind, mechanical as in the machines also can do it. It does not require much. If you know, and you can follow an algorithm and the method will be completed. What is its goal? The goal is to compute the truth values of the truth functional compounds. Okay? That is the goal. Typically, it is a table unlike other table. This has closer connection with the mathematical tables, and we will show you examples. We will show you in a second. Who brought it in is an interesting answer. In 1917, the truth table procedure was invented by Ludwig Wittgenstein. He was an engineer who converted into philosophy. So, he did his PhD in philosophy after doing his engineering degree. As part of his dissertation in PhD, actually this truth table was devised. This Wittgenstein, if you recall my lecture on the history of symbolic logic development, then you will recall that Bertrand Russell is the founder of symbolic logic, and under him Wittgenstein was one of the students, PhD or doctoral students, and he invented the truth table to enable Russell's propositional calculus to mechanically compute the truth value of the compound propositions. This was the goal, and this is how we got it. Truth table was also independently invented by Emil Post in 1921. So, 1917 Ludwig Wittgenstein did it, but independently Emil Post also did that, and this somehow changed the contour of mathematical logic. So, we are going to take a look into this procedure closely, and we are going to learn it soon. So, how to form a truth table? We know now what the truth table, who invented this and so on and so forth, but how to form the truth table? Where do we start? What do we do? First, note that the truth table is composed of rows and columns. So, you are going to have certain number of rows, certain number of columns. If you are asking how many rows are going to be there in the truth table, the answer is that there is a formula for that, and the formula is 2 to the power n, 2 to the power n, where the 2 stands for the number of truth values allowed in your system. Remember, propositional logic domain believes in only 2 truth values, truth and falsity. Hence, you are going to have 2, and the n stands for the number of discrete simple propositions in the compound proposition. Okay. So, together here is the formula 2 to the power n, where 2 is the number of the values and n is the number of the number of discrete simple propositions present in the compound proposition. Let us take an example so that we can clearly understand. Suppose we have B dot A weight C. These are all propositional constants. How many discrete simple propositions we have? 1, 2, 3. So, how many rows, if I am going to construct a truth table for this, how many rows am I going to have? The answer is 2 to the power 3, which is 8 rows. Does it help? So, if you had on the 104 discrete simple propositions, how many rows you are going to have? 2 to the power 4, namely 16. So, this is how to compute how many rows you are going to have in a truth table. It depends on the number of simple propositions. It also depends on the number of truth values that your system allows, 2 to the power n in our case. Okay. Next is how many columns. Now, that answer is not going to be obtained through any formula, but you have to understand what. So, the answer to this question, how many columns, we have to say depends. Depends on what? Depends on, first of all, the composition in the statement. What kind of complexity you have in the compound proposition. You will see that you have to assign columns for each of those little bit of components. Okay. So, that is there, plus there is a certain sequence in which you are going to build the truth table, and we will show you that. So, depending upon all these things, the number of columns you are going to require is going to be fixed. So, let us see first of all, and we will take examples also, but let us proceed anyway. But does not matter how many columns you are going to have, what you must have in terms of columns are the reference columns. Reference columns. So, these are going to be the very first few columns in your truth table. What you need to do is to pick up on the simple statement symbols and arrange them in an alphabetical order. Alphabetical order in the way they appear in the alphabet series. Remember, you are talking about the constants or the variables, and they are all alphabets. So, you need to follow the alphabetical order in which they come. Let me take an example so that you understand. Here, for example, suppose we have the same proposition B dot A wedge C. How many distinct simple proposition symbols? B, A, C, 3. So, the first 3 columns belong to these symbols, and they are going to be arranged in an alphabetical order, not in the way they appear, but in the alphabetical order. So, the first column belongs to A, second one belongs to B, third one belongs to C. Okay. So, that is the first thing to understand, that you need this reference columns to start with. Once you have them, the reference column, then there is this question about distribution of truth values to these simple statement symbols, and there is a certain way to do that. Once these symbols are alphabetically organized, then the first statement symbol gets R by 2 rows of consecutive T's and R by 2 rows of consecutive F's, where R stands for the number of rows. Remember, you already know how many rows there is going to be, that is 2 to the power n. So, then you know how many number of rows you have, but the first symbol gets half of that consecutive T's and consecutive F's. All right, that is the first thing to know. The first statement symbol gets R by 2 rows of T's, R by 2 rows of F's. The second symbol gets R by 4 consecutive T's and R by 4 consecutive F's, and the third symbol gets R by 8 consecutive T's and R by 8 consecutive F's, and so on and so forth, until all the statement symbols are exhausted. This is how we go. If that is already clear to you, wonderful. If not, we will take an example. So, here again we go back to our example of B dot A wedge C, A well C. You know that there is going to be 8 rows here. So, the first symbol, which is your A, right, that is the first statement symbol, it is going to get 8 by 2 consecutive T's, 8 by 2 consecutive F's, that is 4 T's and 4 F's. Second symbol is going to get 8 by 4, that is R by 4, that is 2 consecutive T's, 2 consecutive F's. So, T T F F, T T F F, until you exhaust the all 8 rows. And the last, the third one will get 8 by 8, that is 1 T, 1 F. So, alternately T F until you exhaust the 8 rows. We will show you examples. And then comes the remaining part. So, this is your how to construct the reference columns, and then what columns do I have to do? The answer is, then you slowly take up the connectives that are present, the components that you have inside, and these are to be computed following the truth tables that I have shown you of the connectives in increasing scope, and for each of these connectives you need to assign a column. So that the connective with the least scope is done first and the connective with the maximum scope is done at the very end. So, automatically you know the main connective is going to be computed at the very end. That is going to be your final column, and the result is to be visible in the final column itself. This is how we construct a truth table. So, there are steps and pretty clear steps how to follow them. Now, let me see whether how far we understood this, whether we understood this, and so on and so forth. So, we will try to construct truth table together, and we will try to see if there are any questions that we can take that may come up in the process. I will try to anticipate them. If not, we will see what to do about them. But here is, for example, a sentence like this one, the one that we already had, B dot A weights C. Remember, this is our whole compound statement, and there are 1, 2, 3 simple propositions. So, there is going to be 8 rows. What did I say? First, we need to organize or arrange the statement symbols alphabetically. So, A, B, C. Take a look what I did next. So, 8 rows, 1, 2, 3, 4, 5, 6, 7, 8, and look at the way the truth values are distributed. So, R by 2, T's consecutive and consecutive F's. This is R by 4, consecutive T's and F's, and this is R by 8, T and F consecutively. So, this is the total truth value distribution, and remember, this is an exhaustive truth value distribution, you can't miss it. There are other ways to distribute truth values, but like I said, this is our way of distributing the truth values, and this exhausts all possibilities, all possible truth values of this. Remember, each row represents to you a possibility, a possible situation. For example, the first row represents to you when each of this is true, each of this is holding up. The last row, for example, represents to you when none of this, neither of this is holding up, all right. And then you see the other columns. Remember, this is our whole proposition. So, in here we have a small component here, A weights C. A separate column has to be assigned to that. How will we figure out the value of this? Well, by looking at this A and this C and plugging in what we know about the well or the disjunction. That is how this has to be filled out. This, on the other hand, is the whole proposition, and which happens to be a conjunction. How are we going to figure this out? Well, we already have the A weights C column here, and then we look into the B column and we do a conjunction of that. We already know the truth table of conjunction. This is how this column has to be filled out. So, if you have done it correctly, then this is how your table is going to look like. Look, remember, the disjunction is true when both of them are true, both disjuncts are true, or one of them is true. So, you follow this through. We are comparing this column and this column. T wedge T is T, T wedge F is also T, 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 F, and but here comes also one of them is F, one of them is T. So, this is T. But look at this row where A is F, C is also F, which is why the value returned A weights C is F. So, this way we have filled out this column. Then comes this conjunction, and for this conjunction I said you need to compare this column with B. B happens to be the conjunct, one of the conjuncts. So, what is happening, and let us remind ourselves how conjunction works. Conjunction is true only when both the conjuncts are true. So, for example, here B is true, A weights C is also true, the value returned under the dot is true. This is also the case where you have both the conjuncts as true, but here B is F and A weights C is true. It does not matter which one of them is false. But if you have one false or both false in conjunction, you are going to value the returned value will be f. So, this is how this column has been filled out. I suggest again that you take this proposition and try to do the truth table by yourself, because I have explained it and you have it here to compare, but this is way to learn, that you do it hands on. We will do another one and see where we stand, but I want you to sort of do it along with me. So, here is the statement. This is A dot C horseshoe tilde D. We are going to do the truth table for this. So, what is going to be the first thing to do? How many rows? How many rows? 2 to the power 3. Again, we are going to have 8 rows. Then we need the reference columns. How many reference columns you need? 1, 2, 3, and in that alphabetical order. First one is A, second one is C, third one is D. Distribute the truth values and then we show the result to you. I will give you just few moments to fill up the reference column. Check it whether this is how you have it. So, 4 T's 4 F's, 2 T's 2 F's, and then TF, TF, TF. And then we need to now build up the table, I said by increasing scope. Now, if you go back to this sentence once more, which connective has the least scope here, the minimum scope? The answer is the tilde D. That is what has, this is a connective. It has the least scope. Why? Because it ranges over only one proposition. This one goes over 2. This is the main connective. So, this is going to be at the last, very last. First, we are going to do the tilde D. So, the next column you might fix it like this, the tilde D column, which is going to be in with reference to the D column. Then comes your A dot C, and then comes the A dot C horseshoe tilde D. And this one, as you know, will have to be filled up by looking at these two columns, and by now we know how to do the conjunction column. This one on the other hand is your horseshoe. Where am I going to look at? We are going to look at this A dot C as the antecedent and tilde D. Please note, this is your antecedent and this is your consequent, because in the case of horseshoe the positioning matters. So, this is your first component, this is your second component. Take a look and try to fill up the column for this. I will give you just few moments to fill that up, and then we compare the result here. Because we are beginners, so we are just learning how to do the truth table. Many of you may have done it in different ways, but all of you may not have done. So, this is our beginning, therefore, we need a little bit of a time to do that. And this is why I said you need to know about the connectives. Unless you know enough about the connectives, how they work, it is very difficult to do the truth tables. So, there is still time that you can go back and look at the truth table of the connectives, but if you have the ready knowledge, then you can work this with me in real time. So, A dot C, the column looks like this. Okay. Conjuncts are only, this is conjunction is true only when both conjuncts are true, otherwise it is going to give you false, return value will be false. So, this is where. Now, we are comparing these two columns to see what to put under the horseshoe. Let us remind ourselves that the horseshoe is false only when antecedent is true, consequent is false. Okay. So, only when, if you find a row where A dot C is true, but tilde D is false, that is when this horseshoe is going to be false. Otherwise, in every other case this is going to be true. If you have done it correctly, then this is how this column is going to look like. Okay. This is the only time the A dot C is true, tilde D is false, and this is when you have the F. Otherwise, in every other case it has to come out to be true. Okay. So, this is our first lesson, and I think I have explained it step by step how to construct the truth table. This knowledge we are going to now apply to ask interesting questions. This is just a mechanical method, but it is important that we learn the method first and that we practice it a little bit, so that when we want to apply to a specific problem, then the method does not become the obstacle. This was the point of doing this module together. I hope you have learned how to construct the truth table, because now we are going to pose interesting questions to this method. The method itself is mechanical, but we can pose interesting questions to it, and we are going to, in the next module onwards, we are going to find the answers to those. Okay? That is how far I will go with this module. Thank you.